Hi everyone. In this video, we are going to learn about searching algorithms. The agenda of today's topic is what is searching, and we are going to learn about different searching algorithms like linear search and binary search. And we are going to compare the algorithms by using its efficiency. First, let's see what is searching. To understand searching, let's play a small game. It is given that we are having some set of fruits and each fruit is hidden by a glass or a cup. And the task is that we have to find out where the fruit orange is. Then how do we check? We go and open each and every cup and see what is inside. If it is matching with orange, our search is successful. If not, we go and open next container. Again, if it is not matching, we will proceed further. We open next cup. Again, it's not matching. We go to the next cup. Yes, we found orange fruit. This is what exactly search algorithm. Finding the given element present in the set of items or not. So we have already seen the video. The game is finding the orange in the given list of fruits. So the target element here is orange. So we have to find out whether the orange is present in this set of items or not. So how we did it? We just go and check each and every item and then compare whether it is orange or not. And if it is orange, we found our target. Else, we won't find the desired element which is orange in our search space, right? So searching is nothing but finding whether the given element present in the list of elements or not. So here the given element is known as target and the list of elements in which we have to find our target is known as search space. So in our day-to-day life, we do this search operation very frequently, like searching for a phone number in a phone directory, searching for a book in a library. So these are the basic search operations which we do in day-to-day life. This search space can be an array or a linked list, or it can be database. So it can be any data structure or it can be a database. So to understand different search algorithms, let's assume that our search space is an array. For example, we are having array like this. So we are representing array using A. So our search space is array which is having 10 elements and target element, let's assume 17. So we need to find out whether 17 is present in the array or not. This is the task. So usually how we do, it's like just like a guessing game. So we just say some random index. For example, index is 2. Then what is the element at index 2? It is 3, means not matching. Then we guess another index. For example, index 8. What is the element at index 10? Means it is not matching. So we do proceed like this until we find the target element. But when we are guessing these numbers, we need to make sure that we are not guessing the same number again. Means we have to remember. If array contains very less number of elements, maybe this random search may be good to go. What about if our data structure is having thousands and millions of records? How we will guess it? It is very impossible, right? So that is the reason we are having some algorithms which do the searching process efficiently, not like just random search. So let's see one by one. So in that first algorithm is linear search. We have already seen the game that how the search is happening. So we go and open each cup and we see what is the fruit inside that, right? So means one after the another we are checking. So first we checked first fruit and then we went to next fruit and then we went to next fruit and finally we found the desired fruit which is orange, right? Similar way in array also we just start with the first element, means which is index 0, and we compare whether the element matches with the target element or not. If it is not matching, we go to the next element and we do again go to next element. So this process continues until we find our target element. So this is what linear search means. We are sequentially searching whether the given element present in the given data structure or not. So let's write algorithm for linear search. Here input is array of integers, right? And target element 17. So we know that array elements are accessed using its index, right? So means we have to start with first index. So initialize I equal to 0, which is first index. So how do we get element at ith index? It is using AI. We have to compare AI with the target element, which is k. So then third step, if AI, so matching means how do we represent equals to, right? If A equals to K, then we found the target element, right? Means we have to return true. So then if it is not matching means else case. If it is not matching, then what we have to do? We have to go to the next element. Means how do we do? We have to increment our index. So these steps will proceed. Either we find our target element, means when we find this here itself our algorithm ends, or else until we have the elements in the array, means until we reach end of the array. So here till when we have to do? Before doing it, we have to do whether I less than size. Assume that size is given as n. If I less than n, we have to do this process. We have to repeat it. So now let's see the time complexity and space complexity of the linear search algorithm. So if you notice it, what are the things we are doing? For example, first element is our target element. Means we are going to get our answer in just order of one time complexity, right? This is best case. And if our target element is not in the array or it is at the end of the array. So worst case, it is order of n. So overall time complexity, what we can say, it is order of n. So time complexity is order of n. And we are not using any extra space, right? We are just comparing. We are just using index, which is constant space, and we are just checking element at each index, and then we are proceeding further. Means it is order of 1. Now let's see different algorithm, which is called binary search. To understand binary search algorithm, again we'll pick the same example, which is searching for orange in given set of fruits. So if you notice it, these fruits are actually arranged in alphabetic order of their names. Apple starts with A, banana starts with B, kiwi, K, orange, pear, and watermelon. You are given a hint that the fruits are arranged in their alphabetic order of their names. And our task is to find orange. So that case, what we do? Let's pick fruit at random position. Means, for example, I am picking fruit at second position, which is banana. So B and orange O. So obviously B is less than O, right? B comes first and then O later comes. That means that orange should be right side of it, not the left side of it, because we are given a hint that the fruits are arranged in alphabetic order of their names. So then we ignore these two, and then only in this we do our search process. Again we pick at random position. Assume that we are picking fruit at fourth position. So then it is pear, right? P and O. So obviously P comes after O. That means that after pear we won't get our orange. Means these two will not be in our search space. So we have already ignored these, and then we have all. So our search space is now only these two. So again we go and pick randomly. Again, instead of picking randomly, why can't we take again middle element of the list, and then we can compare, and then we ignore half of the search space. Here it is given that the fruits are arranged in alphabetic order of their names, means there should be some ordering to apply binary search. So now let's take an array which is already sorted. For example, this is the array and it is given that we have to find out 17, whether 17 is present in the array or not. Now let's apply whatever we have done here, but instead of picking random index, every time we pick middle index of the search space. So here size is 9. So what is the middle index here? This is the middle index. Then we compare 7 and 17. We know that 7 less than 17, right? It means that before 7, obviously we won't find 17 because the elements are sorted in nature. So we won't find our answer in this space, right? So we can ignore this completely. Now this is what our search space. Then again we have to do the same process. So in this middle element is either 17 or 19, right? We have considered 19 as the middle element. That case we compare 19 with 17 again. So obviously 19 greater than 17. That means that 19 and after 19 elements, definitely we won't find our target. We are going to ignore these elements. Now our search space has become only this much. So now what is the middle element? So we are considering if two elements are middle element, second one, right? Means this is the middle element. So that means 17 and target element is 17. So what is the relation between 17 and 17? It should be equal, right? So that means that we found our answer. So every time actually we are reducing our search space by half. First time half of the search space has been ignored. This much has been ignored. And second time this much has been ignored. This process repeats until we find our answer or we are done with all the elements of the array. So now let's write algorithm for this binary search. Input is an array of n integers and target element is k. Now let's write algorithm. We have to find out middle element. So how do we find out middle element? We need to know what is the lower index and what is the upper index, right? So this one we can consider as low and this one we can consider as high. We have to take two indices because one for low, another one for high to compute middle value, and then we have to ignore half of the search space, right? So initialize low to 0 and high to length minus 1. So it is 8. So n minus 1. So second step is condition. When we have to stop it, we'll fill it after we perform this. So let's see what should be the condition here. So first let's write what exactly we have done. So we have to compute middle index, right? How we are computing middle index? Compute mid, which is low plus high divided by 2. And once we compute middle index, we have to compare element at middle with target element. So compare A mid with K. If it is equal, first case is if it is equal. If A mid equal to K, then we have to return true. Else there are two possibilities, right? One possibility is AI less than 17 or AI greater than 17. So this case AI less than 17, right? Else if AI less than K, so 7 less than 17. We know that our target element should not be part of this first half, right? Means our low should point from mid plus one element and high is as it is, because we are going to ignore first half of the search space. So if A less than K, low equal to mid plus 1. So else A is greater than K, right? So second case what we have done, we again computed mid, which we assumed like 19, right? So 19 greater than 17. So this means that right part from mid to high, we won't get our target, means we have to reduce high to mid minus 1. So this is the case high equal to mid minus 1. So this continues because lower index should be less than or equal to high, means these steps continues until this is satisfied. So our second condition is if low greater than high, we are going to return false. So step 8 is repeat 2 to 7. So I hope algorithm is also clear. Now let's see time complexity. So if you know, first initially our search space is of size n. So here we are taking order of 1 because we are just comparing middle element. Then our search space is going to become off. Then again order of 1. Then again n divided by 2, n by 2 divided by 2. So here we are taking again order of 1 time. Then n divided by 8. Here also again we are just comparing and then proceeding further. So at some iteration I is going to be n divided by 2 power I, which we are going to find the answer, right? That means that our I equal to log n base 2. So the time complexity is log n base 2. Space complexity. So space complexity of binary search algorithm depends on its implementation. So here we can use either recursive mode of implementation or iterative mode of implementation. So recursive we are using, obviously there is a recursive stack will be used which will take order of n, but if it is iterative mode it just takes order of 1. So order of 1 or order of n I'll mention for now. When we write code for these algorithms, that particular time it will be very clear why it is order of 1 or order of n depending on the implementation. So now let's talk about comparison of these two algorithms. So in linear search, elements can be in random order. But in case of binary search, the elements should be in some ordering. So the example is like sorted order. So linear search is also known as sequential search because we are checking each and every element and then we are proceeding further. So this is also known as sequential search. But in binary search, every time we are reducing half of the search space, right? And we are achieving log n. So that's the reason the binary search algorithm also known as logarithmic search. So we have seen already time complexity. Worst case is order of n. And in case of binary search, order of log n. So linear search, for example, you are having very less number of elements, then linear search is good to go. So this is efficient when search space is smaller in size. But whereas binary search, this is efficient irrespective of size. To understand why binary search is more efficient, let's take small use case. So for example, we are given an array which is not in sorted order. So input is just an array. So in case of linear search, any order is fine. But in case of binary search, we have to sort the array. There is no time complexity here. Here, if we are taking time complexity will be order of n log n. And then searching for an element takes order of n. This is takes order of log n. So this is searching for one element, right? So for example, this search operation we are doing very frequently in our search space. So assume a worst case, it's like a n cube times we are going to search. So every time it is taking order of n means n cube times how much time it will take? N cube into n, which is order of n to the power 4. So now let's see here. So every time it is taking order of log n means overall it will take n cube log n, right? And sorting is only one time, right? Plus n log n. So this means that it is going to be order of n cube log n. If we see now n to the power 4 is greater than n cube log n, order of n cube log n, right? So this way, if we are having frequent such operations, that particular time sorting is not a problem. We can sort it only one time and then we will achieve better results going forward when we are having frequent such operations. So that's the reason binary search is very efficient algorithm. So I hope this comparison is also clear to you. So in next video, we're going to write code implementation using Java programming language. And the implementation for other languages has been given in the description. Thank you for watching. Stay tuned. Happy learning.